Dear students, under the lecture series on complex analysis, we are learning about complex integration. Now, here we have the first theorem under complex integration, which is known as Cauchy's theorem. This can also be called as Cauchy's fundamental theorem. The statement goes like this: let f be a function which is analytic at all points inside and on a simple closed curve C, and f dash of z be continuous. Then integral over C f of z dz is equal to 0. So now, considering f to be an analytic function inside and on a simple closed curve C, and the function f dash of z be continuous, we have to prove that the integral of this function over the contour C with respect to dz will be equal to 0. Now for this, let us consider a closed region first, and let us represent it as capital D. So let capital D be the closed region consisting of all points consisting of all points interior to C together with the points on C. Now let us represent this as a diagram. So let this represent the curve C. So now we are considering all points interior to C and also together with the points on C. So this is the curve C. So the points lying on C is considered. Also the points interior to C is also considered. So now we are going to consider a region which that is a closed region capital D. So which consists of all the points to C, that is interior to C, together with the points on C. So we consider that as region D. Now we consider a complex variable z which is equal to x plus iy. And what will be dz? It will be equal to dx plus I dy. Also we know that f of z represents the function of a complex variable which will be in the form u plus iv. So now this is a complex variable and this is a function of a complex variable. Now we will consider this integral which we have to prove, that is this integral which we have to prove to be equal to 0. So we shall consider the left hand side of this integral. So then the integral over C f of z dz which we have to prove to be equal to 0. So we shall consider this first. So what will this be equal to? Now we shall substitute f of z over here. So this will be equal to integral over C. What is f of z? It is u plus iv multiplied with what is dz? It is dx plus I dy. Now we shall multiply these two. So this will be equal to integral over C. So u multiplied with dx plus u multiplied with I dy. So I u dy plus I v multiplied with dx. So I v dx plus this I square v dy. Now we know that I square is equal to minus 1. So this integral will be equal to integral over C u dx plus, from these two terms I can be taken in common. So we get u dy plus v dx, and here I square is minus 1, so minus v dy. Now further, gathering the real parts and the imaginary parts together, we get this to be equal to integral over C u dx plus I mean u dx minus v dy. So this will be minus v dy. This will be the first integral plus imaginary part I integral over c. We are in fact separating the integrals also. So I multiplied with this, that is u dy plus v dx. So therefore integral over c f of z dz is found to be equal to integral over c u dx minus v dy plus I multiplied with integral over c u dy plus v dx. So let me take and write that, and let me mark this as equation 1. Now each of these integrals we will evaluate separately by using Green's theorem. For this, first we have to state the Green's theorem. So what does the Green's theorem say? So by Green's theorem, we know that integral over c m dx plus n dy. So this will be equal to integral over c dou n by dou x minus dou m by dou y and then dx dy. So this is what we have by Green's theorem. So applying this theorem in our proof, that is in this first integral we have to apply Green's theorem, and for the second integral also separately we have to apply the Green's theorem. So now we will see for this first integral. In this first integral, let me just take and write this once again so that it will be easy for me to show in one lecture. So let me take and write this. Now that equation 1 I have taken and written here. Now we will compare this first integral to this. That is at the place of u, that is at the place of m, we have u for this integral. So m dx plus n dy. So at the place of v, we have minus, at the place of n, we have minus v. So let's write this, this integral first. So integral over c f of z dz will be equal to, now this integral will change as integral over c. Now m dx plus n dy. So we have to apply this. So it will be integral over c. First is dou n by dou x. N is what? Minus v here. So n is minus v. So it will be minus dou v by dou x. And then minus m is u. So m is u here. So minus dou u by dou y. And then dx dy plus, now this integral we will write I multiplied with integral over c will be there because we have here also. Now this is md, so here it is, this will be n because m dx plus n dy. So this should be actually rewritten as v dx plus u dy in this form. So m will be here equal to v. And what will be n? N will be equal to u here. So using that, so integral over c dou n by dou x. So it will be dou u by dou x minus dou m by dou y. So dou v by dou y and then dx dy. Now we are going to make use of CR equations here because we know that the given function f of z is analytic. So when a function is analytic, it will satisfy the CR equations. So let us write that. So the CR equations are ux is equal to vy and uy is equal to minus vx. So what does ux equal to vy mean? It is partial differentiation of u with respect to x, and that is equal to partial differentiation of v with respect to y. So this is what we have in the first CR equation. And in the second CR equation, uy, that is partial differentiation of u with respect to y, is equal to minus partial differentiation of v with respect to x. So this is the second CR equation. Now we shall use these two equations over here. So what will happen to this integral? So we get integral over c f of z dz to be equal to integral over c. Now what is minus dv by dx? That is minus dou v by dou x. So minus dou v by dou x, this CR equation when we use, it will be equal to dou u by dou y. So it will be dou u by dou y. And then we have minus dou u by dou y dx dy plus I multiplied with integral over c. Now what is dou u by dou x? So using the first CR equation, so this one, we know that dou u by dou x is equal to dou v by dou y. So we can substitute that. So dou v by dou y minus dou v by dou y already we have here, dx dy. Now we see that these two terms are same and so they become 0 on subtraction, and similarly this also, and therefore this right hand side completely becomes 0, and therefore we have obtained that integral over c f of z dz is equal to 0. Hence the theorem is proved. So I hope you would have understood how to prove the Cauchy's theorem when the function f is analytic and f dash of z is continuous. So therefore we are done with the proof of the theorem that integral over c f of z dz is equal to 0. So kindly follow the next video lecture in order to learn about Cauchy's integral formula and also problems under them. Thank you.